this short video, we are going to talk about how to identify and fix a few other common visualization problems. So the first suggestion is to use semi-transparency or gradients to make all data points visible. Let's talk a little bit about this. So one of the things that it's fairly common to see is that authors who are creating dot plots or scatter plots sometimes do this in a way where there are many overlapping data points. And whenever there are overlapping data points, they're in the same shade and they're solid. And so that means that they're on top of each other and we can't really see how many data points are there. And so when we looked at this phenomenon, we found this this was looking at a sample of papers published in the top 25% of peripheral vascular disease journals in 2018. So amongst papers that had dot plots, we found that 46% of them had this problem. So the data points were in a single line. This is actually called a strip plot and not spread out, and therefore we couldn't really see overlapping points. For scatter plots, we found this problem in about 88% of papers that had scatter plots. And the flow cytometry plot is essentially a scatter plot with really a lot of data points, a very high data density. So we also found this problem in about a quarter of the papers that had flow cytometry plots. So let's talk about how we solve this problem. So the thing that we're going to do if we're working with a dot plot is to use a strategy called symmetric jittering. And you can see a variety of different techniques that we might use here outlined, going from A, which is our ineffective graph, all the way to our most effective graph, which is the symmetric jitter. But we'll walk through these one by one. So in our ineffective graph, we have a simple strip plot. The data points are on top of each other. We can't really tell how many data points are in these very dense regions, which makes it a little bit complicated to determine what the data distribution might be. One strategy we could use would be to decrease the point size slightly. We don't want it to be too small because then it's hard to see the data points. But in this particular data set, that doesn't really help us very much. These data points are still overlapping. Our third option is to make the data points semi-transparent. So now regions with more data points show up darker than regions with fewer data points. And this is a helpful strategy, but again, if there are too many data points, then at some point that region will stop getting darker, it will be fully saturated, and it can still be a little bit hard to assess the data distribution. A next strategy that we can use is called random jitter. And so it's important to remember here that these x-axis variables are categories or groups. And so this is not a measured value of continuous data. So with random jittering, we simply spread out the data points a little bit along this x-axis or grouping variable. And we do that by adding some random noise. And you can see here that this reduces the amount of overlap. It won't eliminate it completely because there's some randomness to what points get assigned which values, and some of them will end up on top of each other, especially if you have a lot of data points, but it does make things a little bit clearer. And then our last strategy is something called symmetric jittering, where we spread points evenly to one side or the other of an imaginary line going through the center of the group. And this is the most effective strategy because it fully eliminates the overlap and it allows us to clearly outline the shape of the data distribution with our eyes, as well as being able to see every data point so we get a better sense of the sample size. Let's talk now about strategies for scatter plots and flow cytometry plots. And these graphs are a little bit different because we have measured values of continuous data on both the y-axis as well as the x-axis. So this value on the x-axis is a continuous variable. It is not a group. And that means that we cannot use the random jittering strategy because then we would actually be moving the measured value of the data point, which would be an inappropriate manipulation. So what can we do? Well, if you have a small sample size, it will probably be enough to simply make your data point semi-transparent so that those regions with more data points show up darker than those regions with fewer data points. If you have a lot of data points, that strategy won't work because your darker regions will be saturated and you won't really be able to see how many points are there. So in this case, you either want to have a black and white gradient or a color gradient. You can either show the data points in your gradient colors with a scale showing what those values represent, or you could have grid lines like you might see on a topography map showing elevation. And those grid lines would show the density of data points within that region or space. Okay, the next thing that's important to do is to identify when you're using a jet or rainbow color map and replace them with colorblind safe and perceptually uniform alternatives such as the Viridis or Cividis color maps. Rainbow color maps are really common in science as well as in popular media. However, they're highly problematic from a visualization perspective, so it's important that we get rid of them and get them out of our science. Let's talk about why. So these are some visualizations created by someone else, Hujun Ji, and they highlight the problem. So here we have the version of the Mona Lisa that we are used to seeing as it was painted. We then have the Mona Lisa converted into a jet color map, and that is followed by a version in a Viridis color map, which is colorblind safe and perceptually uniform. So rainbow color maps are not great for colorblind people. They create some problems for a colorblind viewer to be able to fully distinguish all of the shades that they need to be able to distinguish between to interpret the data. However, rainbow color maps also create problems for those of us who have completely normal color vision. And the reason for this is that they create excessive levels of contrast where none exists. The reason that this happens is because our eyes react much more strongly to the oranges and reds than they do to the blues and greens. And you can see this in these three versions of the figure here. So if I look at the normal version and the Viridis color maps, I can see that the chest and the face region are a bit lighter compared to other parts of the figure. But when I look at this in the jet color map, these regions really, really stand out because my eye responds so strongly to these red and orange colors. And so this again is not real. It's simply a function of the way that my eye is responding. And these are creating visual artifacts by amplifying contrast and making it appear much larger than it actually is. And the result of that is that we interpret the data incorrectly. So if you are using rainbow color maps, convert your figures over to a colorblind safe and perceptually uniform alternative. The next thing that's important is to choose colors that are accessible for colorblind individuals. So why is this important? Well, data suggests that the most common form of color blindness affects up to 8% of men and 0.5% of women of Northern European ancestry. And so if you think about all of the people that your paper has to go through before it gets published, you think about your co-authors, your reviewers, your editors, all of these people, once you add them all together, it's likely that at least one person in that group is going to be colorblind. And by the time it gets to your readers, absolutely, there will be many of them that are affected by colorblindness and are unable to understand your data because of the way that you've chosen to present it. So what can we do to fix this problem? Well, you might be thinking, okay, I have normal color vision, so how can I tell whether my figure is colorblind accessible or not? One can use a variety of different free tools to adjust the colors on your screen to simulate what a colorblind person would see. These are simulations. Every colorblind person is different, but they will give you an approximate sense of what someone might see. So here, for example, is a picture of a little lizard thing on a plant, and I can see what this would look like for someone with normal color vision, with deuteranopia, which is the most common form of color blindness, and tritanopia, which is the least common form of color blindness. And I can see that this red-green color combination is a problem for someone with deuteranopia because reds and greens look the same, so the lizard now blends in with the plant. Whereas for tritanopia, this particular color combination isn't a problem. One example of a free tool that you can use to simulate would be Color Oracle. And I've provided the web address here. It'll take you about 30 seconds to download. It will install a little wheel on either usually the top or the bottom bar on your main screen window. And you can click on that wheel to change the colors on your screen to reflect what someone would see if they had one of the 3 forms of color blindness. Okay, one of the places where this is really commonly a problem is in microscopy. So let's talk a little bit about colorblind accessible color combinations for microscopists. Green and red, we just talked about, is highly problematic for people with the most common form of color blindness. These 2 things were blurred together, and so you can see that our co-localization here does not work at all for someone who has the most common form of color blindness. Another combination that people like to use is green and blue, and here we can see that that works okay for someone with the most common form of color blindness, but doesn't work at all for someone with the least common form of color blindness. Cyan and magenta is a good colorblind accessible color combination. It works well whether you have the least common or the most common form of color blindness. Some scientists are using for example, green fluorescent protein that shows up as green, and they would like to stay with green so that that channel can be shown in its natural color. This is a combination that also works reasonably well for someone with the most common as well as least common form of color blindness. Okay, I'm not going to talk too much about this today because we had an entire session on flowcharts, but this is just a reminder that you want to include a flowchart in your study to help readers understand your study design, as well as assess the number of excluded observations, the reason for exclusion, and the risk of bias as a result. Okay, the next important point is to avoid using pie charts. And so here I have an example pie chart. I'll just give you a moment and I'm going to ask you to rank the sections in this pie chart from smallest to largest. And you can just write down your numbers on a piece of paper that you have close by. Okay, hopefully everyone has now had enough time to do their ranking. Here I have the same information that is presented in a bar graph, and I'm going to ask you to do the same ranking and see how well you did and whether you got the right answer. And I also wanted you to think about how long it would take you to do this using the bar graph version compared to the pie chart version. So generally what we would find if we were doing it in a class was that some of you were able to get the right version from the pie chart. However, almost everyone or all of you were able to get the right version from the bar graph, and it took you much less time. So our eyes are much better at comparing lengths than they are at comparing angles and areas, which is what we need to do to evaluate pie charts. Pie charts are generally not recommended simply because our eyes are not very good at evaluating angles and areas, and that we need to assess the slices of a pie. And pie charts are particularly problematic when you have something like this, where you have a lot of slices that are very similar in size, or when you just have a very large number of slices. Then it gets increasingly difficult for readers to tell what's going on. So when should you use a pie chart? Our eyes are actually reasonably good at recognizing proportions that are close to 25, 50, 75%, or 100%. So pie charts can sometimes be okay if your proportions are close to those values. My students also like to mess with me, so they send me things like this. So we have identified 2 other situations in which it's acceptable to use a pie chart. You can use a pie chart to illustrate the sunny versus shady side of a pyramid, as is shown here, or the percentage of a pie that you have eaten. Okay, our last point in this section is that it's important to avoid 3-dimensional graphs when you have 2-dimensional data. Let's take a look at this example. So here we have a figure where the 3rd dimension doesn't really add anything. And you sometimes see reviewers do that, or authors do this because they think it makes the data look better or more interesting. Actually, what it does is it makes the data more complicated because readers get confused. They don't know whether they should be looking towards the, they now have to follow around this corner to figure out what the value is, and they're not sure whether they should be reading from the back of the line or the front of the line. And that makes the values very hard to estimate. So you should never use three-dimensional graphs when you have two-dimensional data. Always stick to the two-dimensional version. Okay, that is all for this section, and I look forward to talking more about this topic in class.